In this video, we'll be going through the Topic 2 practice booklet, so you can use it to fill in any answers you didn't get in class or to catch up on any lessons you've missed. So question 1 is about non-renewable energy sources, and we've got what waste products do each of these types of power station emit, or what environmental problem, and then what environmental problem do they then cause. So for oil, you get carbon dioxide, and to get the marks you need to mention that it causes increased greenhouse effect, global warming, or climate change, something along those lines. For nuclear, you need to talk about the storage of the radioactive material, so it has to be stored safely for a very long time, or you could mention specific problems linked to storage or leaks. And then coal causes sulfur dioxide, and this sulfur dioxide causes acid rain. 1 mark for each. Question 2, we are talking about coal, oil and gas again, and 4 different gases that they produce. And we need to use the information in the table to answer the following questions. So which one has the least impact on global warming? So global warming is going to be caused by carbon dioxide or carbon monoxide. So we are going to say the least impact is from gas. So you get 1 mark for gas, and because it produces the smallest amount of carbon dioxide or carbon monoxide, or the least amount. You can't just say it's a small amount, you have to directly compare it to the other two, so it's the smallest. And then which one causes the least acid rain? Again, it's gas, and this is because it's got the least amount of sulfur dioxide, which causes acid rain. The next part of lesson 1 is on renewable energy instead of non-renewable energy sources, and we have got 2 different types of energy sources here, wind turbine and versus a nuclear power station, which is our non-renewable. We're going to compare them, and we've got a lot of data there. So first part, calculate the number of wind turbines that we need to produce the same power as 1 nuclear power station. So for this question, we are looking at power, because it says the same power. So we're going to look at the mean power output. So we have 2 megawatts produced by a wind turbine and 2,000 megawatts compared with a nuclear power station. So we need to work out the difference between them, but by difference between them in terms of multiplication. So we're dividing 2,000 divided by 2, 1,000. So we need 1,000 wind turbines, 1,000 times 2 to get 2,000 megawatts. So we need 1,000 wind turbines to get the same as 1 nuclear power station. The next part, calculate the land area needed to produce the same power as 1 nuclear power station. So we are going to use that answer from above because we've got 1,000 wind turbines, and it's an error carried forward mark here as well. So if you got the first one wrong, you'd still get this one right if you did the correct method. And then we need to have a look at how much space it needs, 0.7 kilometers squared. So we times it by 0.7, so you get 700 kilometers squared. And then part I, we're still talking about the same power again, so we are going to use that 1,000. How many wind turbines every 60 years to produce the same power as 1 nuclear power station? So first thing is going to compare the lifetime. So we need 3 lots of wind turbines to reach the same amount of time as 1 nuclear power station. So we do 60 divided by 20, 3. So we need 3 different life cycles of wind turbine because one stops working every 20 years. So we'd need to replace it, 3 lots of wind turbines to get up to the 60 years. But we also talked about 1,000 earlier. So we're going to times that by 1,000 because that's how many we need to reach the power as well. So it's 3 times 1,000, 3,000. This is quite a challenging question. And the last one, state one advantage of producing electricity by nuclear power compared with wind turbines. I think the easiest one here to say is wind is unreliable, whereas nuclear power can run all the time. All the other answers that are in the mark scheme are on the next slide. And for our extension in lesson 1, we are looking at photovoltaic cells. That just means solar panels. And we're looking at the amount of energy generated in every month. Can we use this figure to validate the claim it should generate 3,400 kilowatt hours annually? So it's worth 2 marks, but it's actually an easy 2 marks. You're just going to add up all these numbers. So the red lines show with my ruler what every bar reaches. So I would always use a ruler for this just to check that you're not reading your graph wrong. So we're going to add 50 for January, 150 for February, 250 for March, April 350, May, June and July are all 500, so we're going to add that 3 times. Definitely write this down just to prove you did it, or you can't prove in the answers how you got it. Plus 450 for August, plus 300 for September, plus 200 for October, plus 100 for November, and plus 50 for December. If you add them up, you get 3,400 kilowatt hours. So it is correct. And for part B, so we have a new figure and it's asking us to describe how the information from figure 2 supports the general trend in figure 1. So figure 2 is just showing us the mean number of sunshine hours, and figure 1 was showing us how much energy we got from our solar panels or PV cells, photovoltaic cells. So they are both a very similar shape. Unfortunately, you don't get the mark for saying they're a similar shape. You need to describe it a little bit better. So between January and May, there's an increase. May to July, it's constant. And July to December, it's decreasing again. Both those graphs show that. That's what you need to say to get the mark. And part II, the Welsh Met Weather Office holds data for the maximum number of sunshine hours. Why can't the manufacturers use this? It would be misleading to use the maximum hours. Instead, they should use something like the average. If you're trying to sell solar panels, you can't just say, because it's a hot day one day, that's what the energy you're going to produce every single day. You can't mislead your customers. Part C, we have another figure, figure 3, and a true false, or which ones are true. So I'm going to go through each one and test them all. So the first one, in December 15, the actual number of sunshine hours was double the expected number. So we can have a look, December 15. So the actual was 30 and the expected was 60. So it does seem like they're double. However, it says the actual is double. And in fact, we've got the expected as double. So that is not true. April 16th was the month that had the most, April 2016 was the month that had the most actual sunshine hours. So if we have a look at April 16, we have a very high number of actual sunshine hours and it is the highest. So that one is true. June, July, August have different expected sunshine hours. So June, July, August, they have the same amount. So that is not true. Jan 16 had the least amount of actual sunshine hours. So if we have a look at Jan 16, it has not got the least amount. That would be December. So that's not true. So we can tell these two are going to be true, but we might as well check. April 16th had 4 times the actual number of sunshine hours. So we have a look at April 16. It's got 200 compared to, it says Jan 16, 50. That is 4 times. So that's true. And there's only 1 month where they're the same, and that is October 15. They are the same. And here's the mark scheme for that lesson 1 question. Lesson 2 was on efficiency. So the first question here, we've got 3 Sankey diagrams and we need to complete them to show the missing energy values. So this is in bold, that means people often miss it. So if you see something in bold, make sure you're doing it, complete the diagrams. So energy in must equal energy out. If you check these two, we'll add to this number here. So again, we've got to work out what number plus 180 will equal 500. So we do 500, take away 180, and you will get 320 megajoules for 1 mark. And then here's the same, 500, take away 350, and you'll get 150 megajoules. Then part B, which type of energy is the input into an oil power station? So we have a look at oil power station. It's chemical energy is our input. And output is the same for all of them. It's the one that goes straight across. It's the electrical energy. All power stations we want electrical energy from. The one with the biggest wasted energy is the coal power station, and it had 350 megajoules of wasted energy. That was going down on the arrow. And how can it be wasted? It could be as heat through the turbine's pipes, or it could be as sound because of the noise that is made by the machines. And then part D, our final part, efficiency of the oil power station. So it's going to be the useful energy divided by the input or the total times by 100. So for our oil power station, we had 170 megajoules was useful. Our input was 500, and we times that by 100, and you get an efficiency of 34%. Lesson 2 is on power stations, and the first part wants us to describe how a power station works using the words in the diagram. So the first thing is we're going to say fuel is burnt in the boiler, and that is done because it boils water into steam. You have to mention steam somewhere in this answer to get the full 3 marks. Steam then turns a turbine, and then the turbine turns a generator, and the generator is what generates our electrical energy. Part 2, Neve says that fossil fuel power stations are 35% efficient, and Jacob says they're less than 30%. Use the Sankey diagram and an equation to explain which one we agree with. So we're talking about efficiency, so we're going to say useful divided by the input times 100. That's the equation we're going to use, and we'll work out the efficiency and then see whose answer we are closest to. So we need to work out the useful energy. So we started with 200 joules of energy, and then all of this is wasted, so we need to take it away and see what we have left. So we're going to do 200, take away 40, take away 80, take away 10, and you'll get left with 70 joules of our useful energy. So that's your first mark there. And then we do 70 divided by 200, that's our input, times it by 100 to get a percentage, 35%. So we'll say we agree with Neve. And here's the mark scheme for that question. Then on to the national grid in lesson 3. So first part says explain how transformer A makes the national grid more efficient. So to get the first mark, you need to say it increases the voltage and decreases the current. And for the next mark, you need to say this is because it reduces energy losses or heat losses in the cables. Part B, transformer A supplies 950 megawatts to the national grid. First, we need to write it down as watts. So you need to have a look at the front of your booklet, and megawatts is times 10 to the power of 6. So you need to put 6 zeros on the end to get that first mark. And then you use that answer in the next question, and you use power is current times voltage, or P is I times V, and you rearrange for current. So current is power divided by voltage. So you take whatever answer you got in the previous question, there'll be arrow carried forward marks here, and divide it by the voltage you've been given, and you should get a current of 2000 amps. Then finally explain transformer B, so that's our step down transformer. It reduces the voltage for 1 mark, and it's to make it safer for that second mark. Part D is a 6-mark question. Discuss how the national grid maintains a reliable supply of electricity to consumers, and it's given you some bullet points. So you need to explain how the demand changes in the day, the types of power station that work continuously, and why hydroelectric power stations are useful. So the first thing you'd say is throughout the day, demand for electricity changes. There's a small demand at night because people are asleep, and there's going to be peaks of demand at breakfast time and the early evening. That answers our first bullet point. Then you want to talk about the ones that work all the time. So these include nuclear, coal and oil, because they take a long time to shut down and start up again. When we have peaks in demand, we need a power station with a quick start-up time, for example, a hydroelectric power station. And we can also use oil and gas power stations to turn on and off to maintain supply, and we can also buy power from other countries if we still run out of electricity. So the next question on power stations is from 2024, and we have got a graph that shows the power demand on a specific day, and the first question says, what is meant by the base load? And it is the minimum power needed. And then the next question asks, what's the peak shown on the graph? So you want to have a look, where's the peak? 40 gigawatts. For part III, we are talking about one specific power station. It has 6 0.3 gigawatt generators, and it is used to provide that additional power once the demand goes above the 35 on the diagram on the previous page, and it can run for up to 6 hours before it runs out of water. Rowan says that this power station can provide power for the whole time. However, it won't provide enough power to get above 35 gigawatts shown in the graph, and you need about 3 gigawatts from overseas. Is he correct? So this seems like quite a complicated question, but it's not too bad. The first thing you want to do is work out how much power this power station can provide. It's got 6 generators, 0.3 each, 1.8 gigawatts. That's the first mark. And then you have a look at when your peak demand is. It's from 4 until 8 at night. It's for 4 hours, and it says it runs for 6 hours. So at the moment, that's all fine as well. But the final thing is how much extra power does it need? And we need an extra 5 gigawatts, and it can only provide 1.8. So we need to find out what's missing. So we do 5, take away 1.8, 3.2. So we need 3.2 gigawatts from overseas, and Rowan says it's about 3, so he is correct. And here is the mark scheme for that question. So the first revision question is about the national grid. And we have a diagram that shows transformer A, and that's the step-up transformer for the first mark, and we've got to explain why we have one. It increases the voltage and decreases the current. This reduces heat losses in the cables. 1 mark for each point of your explanation. Then part B is talking about the National Grid Control Centre. So we have all of the energy coming from all the different types of power stations and the UK demand. So the first thing we need to work out is asking us about the percentage imported, but how much is imported. So we need to add up all these numbers first. 2 add 6, add 16.8, add 5, add 0.4, 1.4 plus 2.9 plus 0.2, and you get a total of 34.7 gigawatts. That's your first mark. We have a UK demand of 35.9. So to meet that demand, we are missing a certain amount, and we need to work out how much. So we work out the difference by taking 35.9, take away 34.7, and you get 1.2 gigawatts. There's our second mark, and it wants that as a percentage. So we do that 1.2 divided by 35.9, and to make it a percentage, we times it by 100, and you get 3.34%. And the last one says we've got a sudden increase. Why do we need pumped storage hydroelectric? And that's because it's very, very quick. So we're going to write it's got a quick start-up time, as opposed to something like a coal or a oil power station that could take quite a while to heat up and start providing electricity. And here's the mark scheme for that question. Our next question starts with part B. Seren states that burning wood produces CO2, so it's harmful to the environment. Do we agree? So trees are carbon neutral. So growing trees absorbs the same amount of CO2 from the atmosphere as they then release when they're burnt. So overall, they're neutral. I would disagree with Seren. They are not harmful to the environment. They are neutral. Then part C, we have a slightly unusual Sankey diagram here, but it's not too challenging. Calculate the total useful output power from this biomass power station. So we've got our input is 20, 3 of it is electrical power to the factory, and 13.4 is heat power to the factory. Both of those are useful in this sense. So we can do 13.4, add 3, 16.4 is useful. The only thing that isn't is this waste power of 3.6. You also could have done 20, take away 3.6 to get the same answer. And then we need to explain, is it 15% efficient? Probably from looking at it, you can already tell that that is incorrect, but we'll do the maths. So it's going to be the useful divided by the input times by 100. Our useful we've just worked out, so you would get an error carried forward mark here. So we do 16.4, our useful divided by 20 times by 100, and that is going to give us a efficiency of 82%. So we're going to disagree because that is obviously not the same as 15%. Part D, the input power is 20 megawatts, and using an equation, how much energy is transferred, and we have a time. So first thing we're going to be thinking here is what kind of equation are we going to use? Energy is equal to power times time. But it's 3 marks. That's our first clue that it's going to be a little bit harder than just timesing the power that we've got by the energy, and that's because of the units. So first of all, for our power, we do have megawatts, 20 megawatts, but if you have a look at our answer, it's in megajoules, so it is fine to leave it in megawatts. The issue is the time in minutes, 60 minutes. We never use minutes as a time unit. We'll be either using seconds usually for joules, or occasionally we use hours when we're talking about domestic electricity. But here we're in joules, so we need to times that by 60, and that's going to convert it into seconds. So it's going to be 3,600 seconds that we use in the rest of our answer. So now we're going to do power times time. We're going to do 20 times 3,600 to get our answer, and it should be 72,000 megajoules. We are now going to need that previous answer in our next question. Burning 1 tonne of wood produces 2,880 megajoules. How many tonnes to get this energy every 60 minutes? So we're going to take our answer of 72,000 and just divide by 2,880, and that will tell us how much, and it is 25 tonnes to get that amount of energy every 60 minutes. Then our next question, we are working out the volume of wood, mass divided by density. Again, we're going to need our answer from the question before. So as you get stuck, just make up an answer so you can use it in your next point, and then you will still pick up marks. There's lots of error carried forward marks in this question. So we're going to have a look. We've got 25 tonnes, so I'm going to put that for our mass. We've got 25 tonnes. And for the density, it's 500 kilograms per metre cubed. 500 kilograms per metre cubed. So there's a clue here though that we're not just using it in tonnes, we want it in kilograms instead. So 1 tonne is 1,000 kilograms. So we've got 25,000. So I've times 25 by 1,000. We've got 25,000 kilograms, and we're going to divide it by 500, and that gives us a volume of 50 metres cubed of wood burned every 60 minutes. And then again, we've got another error carried forward mark as we go into the last part of this question. Each tree produces 5 metres cubed. How many trees to get that 50 metres cubed? We do 50 divided by 5. We're going to need 10 trees to be burned every 60 minutes. And here's the mark scheme for that question. As you can see, lots of error carried forward marks, ECF, ECF, ECF. So if you can't do part 1, just keep going with a made up number. The first part of this revision question asks what's the main disadvantage of relying on energy from wind turbines, and that's that they're unreliable because it's not always windy. Part B is talking about a wind farm in Germany. It's saying that the mean power used by homes in Germany was 0.43 kilowatts in 2017, which is the lowest on record, and you need to suggest why that is. And that could be because we have more efficient appliances, it could have been a warmer year than usual, so less heating was used, or you could suggest that the homes were more insulated than previously. All of these would lead to you using less energy than the year before. Part II, I've picked out some relevant data for this one, is saying how many homes in 2017 could be supplied with that power station. So the overall output power of the power station was 16 megawatts, and each home used 0.43 kilowatts. So we need to do one divided by the other to work out the number of homes, but they need to be in the same unit. We've got megawatts and we've got kilowatts. So I think the easiest thing to do is to convert both of them just into watts. So megawatts is times 10 to the 6, and kilowatts is times 10 to the 3. And you can just write it like this and put it in your calculator like this. So if we work out the overall power, divide it by the amount of power used per home, we will get the number of homes used, and it's 37,209 homes. And then part C is a little confusing because you need to understand the difference between energy and power, and quite often we do use the words fairly interchangeably. So it's talking about our wind turbines have a maximum power of 13.6, and they can provide energy to the water as we pump it up higher for our hydroelectric storage system, and then we generate a larger power from our hydroelectric system than we do for our wind turbines as we release our water. By considering the equation, power is energy transferred divided by time, explain why their claim is true. So you need to realize they both have the same energy. The pumping of our water up to the top and generating the energy. That's because energy cannot be created or destroyed. However, we end up with a higher power because when we release the water, it's released over a shorter time. So we've got the same energy, but a shorter time, and you end up with a larger power for our hydroelectric. This is quite a confusing idea, so do not panic too much if you don't get it. And here's the mark scheme for that question. And then our last page has basically got two forms of a very similar question. So the first part is explain the role of transformers in the national grid. So step up transformer increases voltage and reduces current to reduce power losses in the cables. And next part of the question is step down transformer reduces the voltage to safer values for consumers. And then D is a very similar question. Explain the advantage of high voltages, and that is because it reduces heat loss in the wires due to the reduced current. And here's the review sheet for this topic.